Now problem 1 and 2 is already done before. You can see it in the playlist of NEET JEE Mains. Now I am continuing with the problems of atomic structure, which is a very important chapter belonging to standard 11. Now what problem 3 is, it is given as show that for hydrogen atom En plus 1 minus En equals to 13.6 into 2 upon n cube electron volt. So this you have to show, you have to prove this relation. Now a condition is given when n is very large. So let us first solve problem 3. Solution of problem 3. Now the energy expression of the atoms which have only one electron is given by the formula that is obtained from Bohr's theory, that is minus 13.6 Z square upon n square electron volt. So this is the expression of energy for an atom having only one electron, since we can apply Bohr theory in single electron species only. So this is the formula, this is the expression of the energy. Now it is given that the atom is hydrogen. So for hydrogen atom we have the number of proton equal to 1, that is atomic number equal to 1. So ENH is given by minus 13.6 upon n square EV. We put Z equal to 1, so it will be minus 13.6 into 1 square, that is 13.6 by n square electron volt. So this is our working formula in this problem. Now what is given in the left hand side is En plus 1 and you have to subtract En from it. So using this expression we can find the value of En plus 1 for hydrogen atom obviously. So it will be minus 13.6 upon n plus 1 square electron volt. So this is the expression of En plus 1 and this is the expression of En. Now what is given in the left hand side is En plus 1 minus En equals to we are putting the expressions. This will be minus and minus, this will be plus. So let us take 13.6 electron volt as common. So we will get 1 by n square minus 1 by n plus 1 whole square into 13.6 electron volt. So see, we are taking 13.6 electron volt as common. So this is plus, so 1 by n square will come before and from it this 1 by n plus 1 whole square will get subtracted. Now we have to simplify this expression within the parenthesis. So it will be, the LCM will be n squared into n plus 1 whole square, and here it will be n plus 1 whole square and here it will be n square into 13.6 electron volt. Now let us expand this a plus b whole square. Only you have to perform this in the numerator, don't do this in the denominator. The reason you will know shortly. So it is n square plus 2n plus 1 minus n square. So n square will cancel. This will cancel. So it will be En plus 1 minus En equals to 2n plus 1 by n square into n plus 1 whole square into 13.6 electron volt. This you will get. Now when n is very large, that is the quantum number which represents the orbit of an atom where the electrons are placed, and when this principal quantum number n is very large, we can write this 2n plus 1 almost equal to 2n. n is very large, so we can ignore this 1 to a good approximation, and also we can write here n plus 1 almost equal to n. So this is not equal to, this is almost equal to. So this is an approximation, but the approximation is good. Putting these approximations, we have En plus 1 minus En equals to this 2n plus 1. So when we put, we will give the almost equal to sign here. So it will be 2n plus 1 almost equal to 2n, and n plus 1 almost equal to n. So it will be n square into 13.6 electron volt. Now it is equal to, so 1 n will cancel out, so it will be E n plus 1 minus E n for each atom obviously. It will be 13.6 into 2, 1 n will cancel out and you will get n cube here, so it will be electron volt. So you see, it is proved LHS equal to RHS. So En plus 1 minus En equals to 13.6 into 2 by n cube electron volt. But this relation is only valid when this condition works, that is when n is very large. Now we will try to solve the next problem, that is problem 4. So this problem is solved. Now we come to problem 4. Here you see the problem is given when a radiation of frequency 7.5 into 10 to the power 14 Hz strikes a metal surface, the maximum kinetic energy attained by the emitted photoelectrons is 1.6 into 10 to the minus 19 joule. Calculate the threshold frequency of the metal. So you see, this is a problem of the photoelectric, of the topic photoelectric effect. Now you have to use the Einstein equation here. Now see what is given. Given is the incident frequency, that is nu, which is 7.5 into 10 to the power 14 Hertz. And the maximum kinetic energy attained by the emitted photoelectrons, that is Ek, that is the kinetic energy max, equals to half mv square, is given 1.6 into 10 to the power minus 19 joule. You see, the maximum kinetic energy attained by the emitted photoelectrons is 1.6 into 10 to the minus 19 joule. So you have to calculate the threshold frequency of the metal. Now in photoelectric effect, we have an electrode here within the discharge tube, another electrode here. No voltage is applied in general condition, only a sensitive ammeter is added to the circuit. Now a alkali metal coating is given on this electrode and light is allowed to fall on this plate. So when the incident radiation having frequency nu falls on the metal surface, if this is greater than the threshold frequency of the metal, then the remaining amount of energy will be carried by the electron in the form of kinetic energy. Now some electrons are superficially placed, it is just at the surface, but some are deep seated. Now the superficially placed electrons will require only the threshold energy, and from this investment it will expend only the threshold amount, and the remaining will be converted to the kinetic energy. So it will be with maximum kinetic energy. But the electrons which are deep seated will expend some additional, will have some additional expenses for bringing this electron from core to the surface. So this equation can be related only with the kinetic energy, with the maximum kinetic energy. So as per Einstein, the equation is given by the energy of the photon which is incident on the metal plate, h nu, equals to the work function, that is the threshold frequency required for the emission of the photoelectron, and the balance amount is the kinetic energy maximum, that is we write here E max, E K, that is kinetic energy, and it is maximum. See, various electrons having various kinetic energy will appear from this plate, but to have the equation, to have equal here and equal to, that is an equation here, we must relate it with the maximum kinetic energy, since the electrons which come from the core, which are deep seated, will expend some amount of the energy from the incident radiation to come to the surface. So the electrons which are placed at the surface, which are originating from the surface only, will have the balance energy, that is h nu minus h nu 0, to be expended in kinetic energy. So for the deep seated electrons we cannot write such equation, since there must be some additional term here, and that will not be kinetic energy maximum. It will have a kinetic energy less than the electrons which are placed at the surface. So this relation, you don't have to think a lot about these things while solving the problem, since if they give you the maximum kinetic energy, just put the formula and proceed. Just for understanding I am telling you these things. So put the values. You see, you have to find the threshold frequency, that is nu 0. So take it to the left hand side. H nu 0 equals to, then it is h nu minus Ek max. So to find h nu 0 you have to take this to the left hand side. So it will be h nu minus Ek max. Now what is h? It is 6.626 into 10 to the power 34 joule second. 6.626 into 10 to the power minus 34 joule second. It is the Planck's constant. Now you have to multiply with the frequency of the incident radiation. That will give you the energy of the incident photon. So it is 7.5 into, you see, 10 to the power 14 Hertz. Now you have to subtract the maximum kinetic energy, that will give you the threshold energy. So which is given 1.6 into 10 to the power minus 19 joule. See, this Hertz means cycles per second, that is per second. So this per second and second will cancel out and it will give you joule, so that you can subtract this joule from this one. Now we must calculate it. So we need calculator here. 6.626 into 7.5. while calculating, please don't put these powers within the calculator. That may cause severe error. So, what you will do, you will just calculate with this initial digits. So, 6.626 into 7.5, that will give you 49.695. So, it is 49.695 into, you see, it is minus 34, it is plus 14. So, it will be 10 to the power minus 20 joule. Minus 1.6 into 10 to the power minus 19 joule. Now you convert this to 4.9695. 4.9695. So you will get a 10 factor here, multiply it to this power. So it will be 10 to the power minus 19 joule. Minus 1.6 into 10 to the power minus 19 joule. Now see, the powers are same. So you have to, also the units are same. So just subtract this 1.6 from 4.9. So it will be 3.6695. Am I right? You have to subtract 1.6 from this one. So this will look like this. Let us check. So it is 4.9695 minus 1.6. So it will give you 3.3695 into 10 to the power minus 19 joule. So you got the value of H nu 0, but you have to find the threshold frequency of the metal. So to find nu 0, you have to divide the right hand side by H. Therefore, nu 0 equals to 3.3695 into 10 to the power minus 19 joule by, you have to take this Planck's constant to the right hand side. So it will be 6.626 into 10 to the power minus 34 joule. And here it is second. Since the unit of Planck's constant is joule second. See, this H nu 0 is this one. So what will be the value of nu 0? You have to take this H to the right hand side. Now joule will cancel out. This second will come to the numerator and it will give you second inverse, that is Hertz. Now this is 3.3695 by 6.626 into this 10 to the power minus 34 will come to the numerator and it will be 10 to the power minus 19 plus 34 and it will be second inverse, or threshold frequency equal to, so you need calculator again. It is 3.3695 divided by 6.626 equals to 0.5085. So it is 0.5085 into, you see here, what will be the value? It will be 10 to the power 15. Now the second inverse will be Hertz. You take 10 factor from this 10 to the power 15, this is 10 to the power 15. 34 minus 19 equal to 15. So it will be, the threshold frequency nu 0 is 5.085 into 10 to the power 14 Hertz. So this is the answer. Now you see, there will be photoelectric effect, that is the emission of photoelectrons will occur only when the incident frequency, the frequency of the incident radiation will be greater than the threshold frequency. It is the criteria for the photoelectron emission to occur. The frequency of the incident radiation must be greater than the threshold frequency of the metal. Then only the incident light will be able to emit the photoelectrons. Now see, the frequency that is required to extract the electrons from the metal is 5 0.085 into 10 to the power 14 hertz, and the incident radiation is 7.5 into 10 to the power 14 hertz. So this is similar, 10 to the power 14 hertz, 10 to the power 14 hertz. Now 7.5 is greater than 5, so here we will get the photoelectric effect. And if this incident radiation is less than this value, then there will be no photoelectron emission. So this is for the knowledge only. So this is about the problems 3 and 4. See the next lecture. Here that in that lecture I will discuss about the problem 5 and 6.